In this video, I'm going to go over how you can write an electron configuration and what it all means. So there's two different methods, and I'm going to show you the method that I think is better first, and that is the periodic table method. There's also the diagonal method, and either one you have to remember certain things. I just think the periodic table method is better because in the long run, when we get into later chapters, I think this will help you understand things more. So if you are doing the electron configuration and using the periodic table method, you can set this up. And what you have is the S sublevels will be in this first section here on the left. So what you can do is 1S, 2S, 3S, 4S, 5S, 6. Now what's good about the periodic table method is when you set this up this way, you see in these S sublevels you can only fit a total of two things. So 2 electrons would fit in there. Now the helium that's over here, you can just assume that it gets set up right here. On the right hand side you now have P. And if you have 2S, you go across, this is 2P, and you just bring that on down. And when you do this periodic table method, we can count up. There's 1, 2, 3, 4, 5, 6. So 6 electrons will fit in this P sublevel. Now, one of the tricky things with the periodic table method is when you go into this middle section, it goes from 4S down to 3D. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons that fit in a D sublevel. And now down here between 6S and 5D, another thing you'd have to remember with this method is 4F and 5F. If you remember the general setup for this, and then it goes from 4S to 3D and 6S down to 4F down here, that's going to help you a lot because now it's easy to do this method from here on out. So say we want to write out the electron configuration for bromine. It has 35 electrons total. What you do with the periodic table method is you start up in the top left and you work your way right. When you get to the end of a row, you start back to the left and go left to right. And you basically just keep following that down until you get down to what you're looking for us is bromine. So you have 1S and there's two things. There's hydrogen and helium. So now you move down to 2S and there's two things in there. 2S2. You go over to 2P and that holds a total of 6 electrons. Then 3S, and that holds 2. 3P holds 6. 4S holds 2. And now we do 3D, and there's 10 in there. And you go across 4P, and you count over 1, 2, 3, 4, 5. 4P, 5. Now, there's an easy way to double check to make sure you have the right number of electrons. Since we're talking about a neutral atom of bromine, it has 35 electrons, so you can count up these exponents. 2, 4, 10, 12, 18, 20, 30, 35, and that's what we wanted to get, 35. Now the shorthand method, if you want to do shorthand, and again we'll do it for bromine, anytime you're doing shorthand, you'll always go to the noble gas that comes before it. So even though it's right next to krypton, you can't use krypton, you have to go to the one before it. So you go to argon. And you put that in brackets. And now you would just pick up where argon left off. So argon ends here. So we pick up down here at 4S2. And follow the same thing going from left to right. And we go to 4P5 because that's where we stop. And now you can double check this again. You have 18 coming from argon. There's 20, 30, and 35. And so that's how you do the periodic table method. If you just remember this general setup, it reminds you, or it basically has it built into it, that it tells you how many electrons fit in each sublevel. Now the diagonal method, which some people prefer this one, and you could do this if you want, but I still think the periodic table method is better. But you can get something like this and set up the diagonal method. That should be like this. So when you set this up, you would have to set it like this. You'd have to remember how to set it up. Now, what's different about the diagonal method is you would have to remember how many electrons are in each sublevel. So for the S's, they can hold a total of 2 electrons. The P's can hold 6, the D's can hold 10, and the F's can hold 14. You'd have to remember that part. So whatever method you pick, there's certain things you have to remember for either method. So let's say we're talking about bromine again, and we know that had 35 electrons because we're doing a neutral atom. All right, well, for the diagonal method, you start in this first box, and you basically draw an arrow from right to left, and 2 electrons fit in here. So you write it as 1s2. And now the next arrow goes through the 2s box, and that holds 2 electrons also, so 2s2. Now you go through 2p, and then 3s, so 2p6, 3s2. When you're doing this, it's easy to start drawing in arrows all over the place and filling everything out. But remember, you only need a total of 35 electrons. Now we're nowhere near that yet, so I can keep going. All right, so now when we're done that arrow, I do 3p, which can hold 6, and 4s, which can hold 2. Now I want to count up what I have so far. 2, 4, 10, 12, 18, 20. And I need a total of 35. So I can go through to 3D. That can hold 10. Now what that tells me is that brought me up to 30 electrons. I only need 5 more. So 4p can hold a total of 6, but it only needs 5. So I do 4p 5. And again, you can double check your work. It's 2, 4, 10, 12, 18, 20, 30, 35, which brings us to this number. Now, if you want to do the shorthand for the diagonal rule, it ends up being a little different, and I think a little more difficult than the periodic table method. Helium would go above this 1s, and if you look at your periodic table now, I'm just taking the stuff that's in the right-hand column, the noble gases, and just filling them in order. So helium would go with this 1x box. Neon would go with the 2p. Argon would go with the 3p. Krypton would go with the 4p, xenon is 5p, and radon is 6p. So say we wanted to do bromine, you would still have to look at your periodic table and get the noble gas that comes before it, which is argon. So you would put argon in brackets, and argon brings you down to here. So now you just pick up what's left after this box. So argon's bringing you all the way through here, so you do 4s. And again, pay attention to how many electrons you have and how many you need. Argon takes up 18 electrons. So that 4s2 brings you up to 20. 3d can hold a total of 10, so now that's 30 electrons. And we're left with 4p. We only need 5, even though it can hold 6, so you do 4p5. And that's how you can do the shorthand for the diagonal method. Now, once you figure out how to write electron configurations, you can write these out pretty quickly a lot of times and get them for any element off the periodic table, which is all fine and good, but you have to know what they mean. Right? If you just write out 1s2, 2s2, 2p6, and you don't know what it means, it's not really going to be all that helpful for you. So once you get an electron configuration, I'm not going to write a whole lot here. You know, you can have whatever. What do the coefficients in front mean? And what do the letters mean? And what do the exponents mean? Well, some of this goes along with the principal quantum numbers. We went over 4 principal quantum numbers in class. When you have an electron configuration like this, it actually only takes 2 of the quantum numbers into effect. So what happens, the coefficients, I'm going to abbreviate here a little bit, the coefficients, they refer to the principal quantum number. All right, and that's referring to the energy level. The energy level is just telling you how far away from the nucleus those electrons are likely to be found. All right, so if you have something like energy level 1, that's going to be closer to the nucleus than energy level 2 or 3 and so on. And this corresponds to the periods on the periodic table. If you look at our periodic table, and certain ones might be different, but the ones that we have in your reference packets, they have those numbers 1 through 7 all the way on the left-hand column. Well, that's telling you a principal quantum number. All right, the letters, the S's, the P's, and the D's and F's, I'll just write S, P, D, F. They are referring to the angular momentum number. Another way this is said is with the word sublevel. This is talking about the shape of an orbital. So it describes the shape So you look at the pictures that I've drawn up here, and S sublevel has a spherical shape, right? It's not a circle because it's three-dimensional, X, Y, and Z, so that's a sphere. The P sublevel has a double dumbbell. I'm sorry, not a double dumbbell, just a dumbbell. It's like a figure eight kind of on its side. The D sublevels, they have a double dumbbell, where you also get the shape, which I'm not really sure how to describe. And then there's also F, and those shapes are really complex. I didn't get any of those pictures, but I'll show them in class, and you can find them online. So that's what the SP and the D, SP, D, and F stand for. They talk about the shape of the orbitals that these electrons are likely to be found in. Now the exponents, they actually don't have anything to do with quantum numbers. The exponents are just telling you the number of electrons in the orbital. So just number of electrons. Like I said, I counted those up for bromine. We needed 35 electrons, so your exponent should add up to that number. All right, that's 2 of the 4 quantum numbers. So the electron configuration only goes along with 2 of the quantum numbers. There's another quantum number that's called magnetic quantum number. All right, and that's talking about the three-dimensional orientation. And that's on the X, Y, and Z axis. X, Y, Z. This does not come up in the configuration. The only time you really have a representation of this is when you have pictures like what's up here. The P sublevel can be orientated on the X, the Y, or the Z axis, which is why it's said to have 3 orbitals, and every orbital can hold a total of 2 electrons, which is why the P sublevel can hold at most 6 electrons. This sphere for the S, that can only be orientated one way. You can turn that thing around on the X, Y, or Z axis, and it's always going to look the same. So it's one orbital, because it only has one way to draw it, and each orbital can hold at most 2 electrons. Now the D, you can do that 5 different ways. Each orbital can hold a total of 2 electrons, so that's why you can hold at most 10. F have 7 orbitals, which means 14 electrons. The last quantum number is the spin quantum number. And this is talking about whether it's rotating clockwise or counterclockwise, is the designation it's said. This does not come up in the electron configuration either. The only time you really see this is if you do an orbital box diagram. And let's say we're talking about something like oxygen that has a total of, 8 electrons? When you get to the 2p, what you do is you fill in each box with an up arrow before you start doubling them up. So the spin quantum number, you can either designate it with a plus 1/2 or minus 1/2, although usually use electron or arrows, up or down arrows. So it's saying one spinning clockwise and one spinning counterclockwise. So that sums up electron configurations and the quantum numbers.